Allow me one moment to grab a charger. We'll start in 1 minute. Okay, we're ready to get, oh, I'm not sure why the screen's not sharing. 1 moment, let me share the screen and then we're good to go. Okay, we're just about ready to get started. Just some announcements and some discussions of things I've been noticing that I would suggest that we address. So first and foremost, I really do want to emphasize next week we will be lecturing the day of the exam. The exams are taken in laboratory. I've noticed in many semesters, attendance usually drops right before the lecture exam. Missing lectures is highly detrimental towards keeping pace with the content in this class. And as you notice, we move relatively quickly through the material. I just want to make sure that everyone is staying up to speed with the material and that there are no issues. Additionally, I would encourage you to attempt the practice exam this weekend, just to get a sense of any concepts that you'd like to address your questions for, and concepts that you'd like further practice on. A lot of the homework that I assign is what I would consider the minimum to maintain pace in this class. It is not necessarily the amount that each individual student needs in order to truly test their understanding, in order to truly practice the material fully. This is just the amount for me to verify your understanding and check up on how everyone's doing. Beyond that, we have services available such as the mentorship program. Students who've been to the mentorship program have benefited immensely from it, both in the pre-lecture assignments and on the quizzes. And we also have office hours and tutoring services via the LRC. So as we continue this lecture today, we'll finish up chapter 3 and really maintain consistent effort, continue showing up to class. I was really impressed that we had 29 people today. It was wonderful. Keep that up, because a missed session will often result in a very confusing return to lecture. Okay, with that said, let's get started with today's session, which we're continuing off on nomenclature and periodic trends and charge preferences. So transition metals are a bit of an oddball with respect to charge preferences. Transition metals will typically adopt a +2 charge in many of their common ions, but transition metals uniquely can adopt a range of positive charges. I like to call transition metals the quote-unquote B group metals, also known as D block metals. So examples of a transition metal would be iron, where iron can form Fe2+, and it can also form Fe3+. So for transition metals, we're going to have to adopt a very special set of naming conventions in order to adequately describe what transition metal ion we are dealing with. Now, thankfully, most main group metals, or A group metals, will adopt a positive charge equal to their group number. For example, magnesium, which is a 2A element, forms magnesium 2+. Let's do a few more, just to make sure we're practiced with this. Let's take a look at aluminum. So break out your periodic tables, and would someone like to volunteer the group number for aluminum? 3A, yep. Aluminum is a 3A metal. So what charge will it form? 3+. Okay, perfect. Let's look at a few more examples here. Let's look at cesium. Would someone like to volunteer the group number for cesium? 1A. Because cesium is a 1A element, let's break out our periodic table just to showcase that. If we zoom in, the first column in the periodic table is the group 1A, and cesium happens to be in that group. Does it make sense where we're getting these group numbers from? Okay. So let's switch over. So cesium likes to form cesium +1 that we write as cesium plus. Let's now talk a little bit about our nonmetals. So most main group nonmetals adopt a negative charge equal to 8 minus their group number. So for example, when we're looking at oxygen, oxygen is a group 6A element. So we'd have 6 minus 8. That would give us -2. So then oxygen likes to form an ion of O2-. Does that make sense? Okay, let's do another example. Let's take a look at nitrogen. I'd like someone to volunteer. What is the group number of nitrogen using your periodic table? What was that? 5A, yeah. Let's showcase where we got that number from. So if we go to the periodic table, again, this one's a bit mean, but nonetheless, so we see a number 15. To get the group number for the elements on the right-hand side, we take 15 minus 10, and that gives us 5A. Does that make sense? Okay. So then, nitrogen as a group 5A element, we take 5 minus 8, and it adopts a charge of -3, or 3-. So nitrogen prefers to form nitrogen 3-. Let's do one more. Iodine. What is the group number of iodine? 7A. Yep. Okay. So then 7 minus 8 gives us -1. So iodine likes to form I-. So far, so good? Okay. So let's unpack transition metals one more time and just talk about them again. I really want to emphasize that transition metals in general can adopt a +2 charge, but they typically adopt a range of positive charges. You can have iron plus, iron 2+, and iron 3+. There is one exception to this idea that transition metals have a variable charge. We call these special types of transition metals with a fixed charge, creatively of course, fixed charge transition metals. Silver, cadmium, and zinc. So Ag for silver likes to form silver plus exclusively. Cadmium, Cd, likes to form cadmium 2 plus exclusively. And zinc exclusively likes to form zinc 2 plus. So for these three transition metals, they only typically adopt one ion charge. You're not going to see multiple different ions with different charges for these fixed charge transition metals. Does that make sense? You're going to have to memorize these three and know their chemical names and preferred ion charge.
These are the only fixed charge ones?
Yes, these are the only three that you'll see in this class. Yeah. Any questions? Yes.
Should we also memorize for the test the ones with barium charges?
We'll talk about how to handle variable charge transition metals, as you're not going to explicitly memorize them, but they have to be named using different conventions. Does that make sense? Perfect. Okay. And can everyone in the back see the slides and hear me okay? If you're having trouble, don't be shy to move up, okay? Okay. So for predicting chemical formulas of ionic compounds, so the total charge of an ionic compound is the sum of the charges of each ion, right? So we're going to add up the charge of every single individual ion, and that will give us the total charge of our ionic compound. Okay, so the total charge is the charge of the cation times the number of cations plus the charge of the anion times the number of anions. Okay, so we're adding up all of our cations, which are positive or negative. Positive, and all of our anions, which are negative. So let's put those symbols in place. Okay, now there's a wonderful little trick associated with stable isolable ionic compounds. So if you can isolate a solid ionic compound, stable, isolable, solid ionic compounds are neutral. That means their total charge is 0. So then we can set this total charge equal to 0. Now, before we start using this formula, let's talk about how do we fill in all of these blanks. That's a lot of variables to have to deal with. Well, we're going to be using our periodic table and periodic trends. So the first step is to figure out the charge of each component ion. So the first go-to is your periodic trends. So periodic trends are perfect for your main group elements. They allow you to predict the charges of ions formed from main group or A group elements. So for cations, you're just going to read off the group number. For anions, it gets a little bit more tricky. You're going to have to take 8 minus the group number. Just to make sure we're all on the same page, what types of elements form anions, negative ions? Nonmetals, exactly. Your anions will be nonmetals, while your cations will be what types of elements? Your cations will, one moment. Your cations will be what types of elements? What was that? Metals, exactly. Perfect. The other thing that you will have to consult if you encounter a polyatomic ion, you're going to need to have memorized the common charges and formulas of all the polyatomic ions in the table that I showed you earlier. Now, there's a third way, and this is to address your question, how do I deal with transition metals? Well, transition metals, thankfully, our naming rules provide us the charge. So names involving metal ions or transition metal ions in particular will include the metal charge. So for example, iron, which is a transition metal. Because the charge of iron is variable, we will explicitly note the charge of iron in this ionic compound. So we'll say it's iron 2 bromide. This Roman numeral represents 2. So then we'd have Fe2+. Let's give another example just for reference. So copper 3 oxide. So what is the charge of copper in this compound? 3, because what does this Roman numeral represent? How many lines do you see? 3, yeah. So this is copper 3+. We'll talk more about reading Roman numerals when we get to naming transition metal containing compounds. Okay, so is everyone clear how we're getting the charges? Okay, once we have the charges, we, of course, will need to determine the charge of each component ion. So let's do an example. So let's suppose we're forming a compound from calcium and bromine. So we're combining and we're making an ionic compound that contains calcium and bromine. Okay? So dissecting this step by step. Calcium, metal or non-metal? Left or right-hand side of the periodic table? Left. So it's a metal. And what is calcium's group number? 2A. So let's show this in the periodic table. So if you pull up the periodic table and you go to calcium, as we've discussed in previous problems, it's in column 2, group 2A. Because it's a metal, going to our printout again, what charge will calcium adopt? 2+. So we have calcium 2+. Wonderful. Let's now deal with bromine. What is bromine's group number? 7A. Again, to showcase this in our periodic table, if we go to the halogens, bromine is in column 7A, group 7A, and is bromine a metal or a non-metal? Is it on the left or the right? Non-metal, exactly, it's a non-metal. That means we're going to get anions. And so, like looking at the charge preferences, 7 minus 8 gives us -1. So we have Br minus, or bromide anion. Does that make sense? Okay. So now that we have each of the charges, so we have bromide anion and calcium cation. This next method I'm about to show you only works if your overall ionic compound is neutral, which is the majority of the ionic compounds you're going to be dealing with in this class. What you're going to do is you're going to take the charge and you're going to move the charge of one ion into the subscript of the opposite ion. Okay? So the charge gets moved down to the subscript of the opposite ion. So then, writing out our formula, we'd have calcium, and how many calcium atoms are indicated? If we cross the charge of the opposite ion, which is bromide, down to the subscript of calcium. 1, yep. So let's put that. Okay, and for bromide, how many bromide ions do we have if we cross this 2+ to the right? 2, exactly right. Okay, so our final formula would be CaBr2. So in effect, as long as we are given the elements, if they're main group elements, we can quickly predict the formula of an ionic compound formed from those elements. Does that make sense? Okay. Now, as a last step, you do want to verify that the total charge of your ions matches the total charge of your ionic compound. Let's just showcase that really quickly. So the total charge should be 0. Okay. What is the charge of our cation? What's our cation in this case? Yep, calcium 2+, so we're going to write out +2. And how many cations do we have in calcium bromide? How many calciums do we see? Calciums. 1, yep. Perfect. Okay, we're next going to account for our anions. What is the charge of bromide? -1, right? We have it right above here, right? So it's -1. And how many bromide ions do we have? 2. Okay, so we have 2 minus 2, and lo and behold, we get 0. So we've checked our work. I encourage you to check your work if you have a spare moment on the exam, because it'll save you a lot of grief. Any questions on this? Okay, let's keep going. So I'll do this next example, and you'll be responsible for the remaining few. So aluminum oxide is composed of aluminum and oxygen ions, or, well, I guess aluminum ions and oxide ions to be exact. So if we're writing the formula, first and foremost, I'm going to write out each of my elements, and I'm going to find their group numbers. So I'm going to go to the periodic table, and I'm going to find aluminum and oxygen. So this 13 isn't the group number. Remember, this periodic table is a little bit mean. You're going to have to take 13 minus 10, and that gives us our group number of 3A. Okay? So then I see that aluminum has a group number of 3A. Yep. What is oxygen's group number? 6A. Exactly. See, oxygen's in this column. Perfect. Okay. Let's go to the printout now. So aluminum is a 3A element and oxygen is a 6A element. Now, to avoid giving things away, I intentionally used a dark color, but is aluminum a metal or a non-metal? So let's look at the periodic table. So remember when I had you memorize the dividing line? So aluminum is on the left of that typical dividing line. So is it a metal or non-metal? Metal. So aluminum is a metal. So then in general, is it going to form cations or anions? Cations. So aluminum is going to form a cation with what charge? Yep, +3. Yep. Okay. Let's now move to oxygen. So is oxygen a metal or a non-metal? Non-metal. Okay. And so then our charge preferences is our group number -8, which gives us -2. What we're next going to do is we're going to take each of our charges and cross them into our subscript to give us 2 aluminums and 3 oxide ions to give us the following formula for aluminum oxide. Now, one thing that I want you to pay attention to here, do we actually truly care about the exact element that we're using in this method? What numbers are we using for this formulaic method? What numbers do we care about? The charges, sure. And where do we get the charges from? What do we care about? Group number. So in this method, the group number is the only thing that matters. So then, as a hint to you, if we have the same charges or the same group numbers, will our formula end up looking just the same? While you're thinking about that, I'd like you to tackle this next problem. For writing a chemical formula for an ionic compound containing Fe3+ and S2-. So iron 3 cation and sulfide anion. And see what that tells you. Okay, so people are definitely catching on to the principal gimmick of this formula. It doesn't actually matter the identity of your atoms when you're predicting the formula. The only thing that matters are the charges. So to showcase what I mean, if we have Fe3+ and S2-, just like our aluminum 3+ and O2-, when we cross the charges, we would end up with Fe2S3, just like we ended up with Al2O3. Same charges for our cation and anion, same formula ratio of cation to anion. So this is how you can write formulas quickly. If you can notice, oh, oxygen and sulfur are in the same group. Oh, aluminum and iron 3+ have the same charges. Okay. So really, the main focus of this example is that you can replace any ion in an ionic compound with another ion with the same charge, and you get a new, equally valid chemical formula. So this is how you quickly write formulas. Any questions on how that works and how this example demonstrates that principle? Okay, I guess I'll continue on then. So, what I'd like you to do is to write out the formulas of these next two ionic compounds. So these are new charge patterns that you haven't seen before and that we haven't done before, but you can apply the same method that we've talked about to write out a valid formula. The one hint that I do want to give you for this following example is that you want the simplest ratio of ions. Yes. Is there a simple ratio that we can get? Yep. So the entire SO4 is one ion. So you put the subscript for the entire ion. Wow. Oh, so treat the SO4 as one giant. So let's talk about this first example. So first and foremost, we have calcium ion, calcium 2+, and as our anion, we have sulfate, which is SO4 2-. So when you're dealing with polyatomic ions, you place the entire polyatomic ion in parentheses, and then you cross your subscripts and charges just like normal. So that would give us, we would predict to have how many calcium ions? Initially 2. And how many sulfate ions initially? 2. For those who are saying 1, you are 100% correct. We just need to talk a little bit about what a chemical formula represents. So when you end up with a ratio of ions, this method only works if it's generating the simplest possible ratio of ions. We want the simplest whole number of cation and anion. So then this 2-to-2 ratio can be simplified to 1-to-1, which would be CaSO4, which we call calcium sulfate. So again, whenever you're generating a formula of an ionic compound, it should be the simplest, smallest whole number ratio of ions. So for this next compound containing scandium and cyanide, we have scandium 3+, Cn-. Would someone like to volunteer a valid formula for scandium 3 cyanide? Yes. Yep, exactly. ScCN3. Exactly right. We cross our charges into the subscripts, and that gives us our formula. Everyone okay so far? Okay, now I'm going to actually have you use the periodic table. So, given that you have an ionic compound containing sodium and sulfur, I'd like you to tell me the formula of the ionic compound using your periodic table and charge preferences. And I'll give you about 1.5 to 2 minutes. Let me move the cursor so it's not getting in the way. Yeah. But our method, when it spits out that formula, the simplest ratio is H2. Yeah, yes. Yes. Yep. Oh, so you have support. So there's 2 to 2. Yes. The examples I have one version are a little bit different. So let's now break out our periodic tables and let's discuss this problem. So which of the following two elements is our metal? Sodium. Okay, so we have sodium, and what is sodium's group number? 1A. Where did we get 1A from? If we go to our periodic table. Sodium is in what group? So, wait, sodium. Oh, 1A. So, we're getting ahead of ourselves, but yes, sulfur. Sulfur is in 6A. Yes, sulfur is in 6A. Perfect. Thank you. So now we have all of them set up. We have the group number of our anions. So we have sulfur, which is 6A. Perfect. Now that we have our cation and anion established, we have our metal and non-metal, let's write out our charges. So because sodium is a group 1A, what charge will sodium adopt? Yep, +1. Because sulfur is a group 6A, 6 minus 8 gives us -2. So sulfur adopts a charge of -2. We next cross the charges into the subscripts, and that gives us a final formula. Yep, exactly, of Na2S. Otherwise known as the formula of sodium sulfide. Does that make sense? Okay. Let's now do a few more examples. This time we're going to use this formula to predict the ionic charge. And the main place that we'll need to predict the ionic charge of an ion is to determine the charge of a metal. More specifically, this method is super useful for transition metals. Why would that be? What's the key feature of transition metals? Can we just look at the periodic table and figure out their charge? No, they have variable charge depending on the compound they're a part of. So just like before, we're going to be looking at our total charge equation. The total charge is the charge of our cation times the number of cation plus the charge of our anion times the number of anion. Thankfully, for the majority of ionic compounds, the majority of ionic compounds are neutral. They have 0 charge. So just like before, we have an equation. Let's fill in the blanks here. So the first thing you're going to do is to figure out the charge of one of your component ions. And we have methods of figuring out the charges of our ions. And the ion that you're going to figure out the charge for is typically going to be your anion, because they have much more, anions often have fixed charges. Cations, such as transition metal cations, have variable charges. So the first thing you'll turn to is your periodic table. You'll use your periodic trends for your atomic ions. Remembering that for anions, the charge is equal to the group number minus 8. And the reason why I have you memorize these polyatomic ions in part is because you're going to be using the common charges of your polyatomic ions in order to determine the charges of your metal, transition metal cations. So that's why you need to know the formulas, names, and charges of all these polyatomic ions. Now, there is one trick for this, and remember how we crossed our charges into our subscripts? We're going to go through this exact same process in reverse. So what you're going to do is you're going to place the subscript for an ion into the charge for the opposite ion. and I'll show you how this works. There's one little caveat that we have to note. If the charge of a single ion does not match the known charge, you need to multiply both charges by a whole number. So let's show what I mean. Let's talk about what I mean. So let's look at this first example. This one isn't even a transition metal containing compound, but it serves as a good test bed for this idea. So when we think about cesium bromide, we can really think about it as we have how many cesiums? How many cesiums do we have? 1. And how many bromide ions do we have? 1. So what we're going to do is we're going to take each of our subscripts and we are going to place them in the charge of the opposite ion. So it's our crossing method in reverse. That gives us, for cesium, what is the charge according to this model? +1. And the reason why that we know cesium adopts a positive charge is cesium a metal? Yes. Likewise, we know that bromide would adopt a charge of what according to this method? So we see the number 1, but using our chemical intuition, we know that bromide's a nonmetal, right? So then, what type of charges do nonmetals adopt? Negative. Nonmetals like to form anions, so it would be Br minus. Now, this clause A may seem pointless at first glance, but it's incredibly important to ensure that your charge predictions are actually correct. So suppose we have cobalt oxide. Again, we have a nice clean 1-to-1 ratio. However, this problem is deceptively more difficult. So if we reverse cross our subscripts into our charges, that would give us a predicted charge of cobalt plus and oxygen -1. Again, why did I assign the positive charge on cobalt? Is cobalt a metal or non-metal? Metal. And why did I assign a negative charge on oxygen? Is oxygen a metal or non-metal? Non-metal. Exactly. Exactly. Okay, now, does anyone notice something wrong with this? Something clearly and obviously that doesn't look right here. So thinking about oxygen, which is a 6A element, we would expect oxygen to form an anion with what charge? 2 minus. So this oxygen 1 minus really just sticks out like a sore thumb. So our way of correcting this is we try to figure out, how do I get 2 minus? So what do I need to multiply my charge, both of my charges by, in order to get O2 minus? What times 1 gives us 2? 2. So I'm going to multiply both of my charges by 2. Key rule, both of them. This only works because the ratio of charges will stay fixed. So our formula will still be valid. If you only multiply 1, you're not creating and you're not describing the same formula, same ratio of ions in the correct charges. So then, at the end of this entire process, we get cobalt plus 2 and O2 minus. And with that, all is right with the world. We're following, whoops, let me zoom in here. We're following ion charge preferences, and we've successfully predicted the charge of our transition metal, which is what? What's the charge of cobalt? 2 plus. That's the entire point of this type of exercise. Okay. Now, there's another way of going about this, and in this case, if you know the charge of one ion, you can also manually solve for the unknown charge by using the following equation. To show how this works in practice, let's use an example of tin tetrachloride, or tin 4-chloride to be exact. I always have to be careful with transition metals because if I give you the name in the formal method, you'll immediately know the charge if you're paying attention. So let's figure out the charge on tin. Why is tin our cation? Is it a metal? Yes. Okay. So using this equation, we have to take -1 times the charge of our anion. And what is our anion in the tin tetrachloride? What's our anion? What was that? Chloride, yep. Cl. As it is a 7A element, what charge does chloride adopt? Yep, -1, Cl minus. Okay, so the charge of our anion is -1. And now how many chlorides do we have in tin tetrachloride? SnCl4. 4. Yep. Okay, finally we're going to divide by the number of cations. How many tins do we see? 1. That gives us a charge overall of +4. Does that make sense to everyone, how to do it algebraically? Now, you're always going to have to remember that this equation has made a critical assumption. What did we assume about our overall charge in this particular equation? What's the overall charge of our compound? Neutral, exactly right. So this equation only applies for a neutral ionic compound. There are charged ionic complexes that can be formed in solution. And in fact, we'll be looking at one just to make sure we're all on the same page. So, before we get to charged complexes, I'd like you to predict the charge of each ion in the following 2 compounds. And you're going to need your table of polyatomic ions that we discussed at the start of class. Oh, you memorized them already? Oh, that's good. Eventually, I'll test this information. So let's take a look at these examples. And just for the record, on the exam, you won't have the table. So as you progress through this chapter, you want to start using your polyatomic ion table less and less. So Looking at hydroxide, OH, this is a textbook polyatomic ion. What is the charge of hydroxide, OH? Yep, OH has a charge of -1. Is everyone clear where I got this OH minus from? Would anyone like me to show the table and scroll up? I'll do it once for this one. Let's go and show you the table. One moment. Here we go. So if we go to our table of polyatomic ions, lo and behold, there's hydroxide as OH minus. Everyone clear where I'm getting these charges from? Okay. So let's go all the way back up. Okay, so we have OH minus. So if we wanted to figure out the charge on tin, let's write our tin. Let's write our hydroxides. We have 4 of them. And then to get the charges, all we have to do is cross the subscript up to the charge. And that gives us 10, 4 plus, and OH minus. Now, before we just go off and write this as our answer, does this match the predicted charge of hydroxide? Does this match? Okay, always do that little mental check if you're using the reverse cross method. Now, you could have actually saved yourself a lot of work here, because as we notice from tin for chloride and tin for hydroxide, do chloride and hydroxide have the same charge? Yes. And do we have the same number of ions? We have the same number of anions in both cases. Do we have 4 chlorines and 4 hydroxides, the same number? And we also have 1 tin. So then, by analogy, because this reverse cross method only cares about the subscripts, you could have immediately said, oh, hydroxide and chloride are exactly the same. If we have the same number of them, tin must have the same charge. This is how most chemists are able to come up with charges very quickly. We aren't manually calculating them. We're reasoning via analogy. And that's one of the skills as chemists you'll develop. Does that make sense to everyone? Does everyone notice if you put them side by side, they look almost identical? Yeah. Okay. So this next one is a bit of a funny question because you don't actually need to use the reverse cross method. You can just write out your answer. Would someone like to tell me why that is? Why can I just write out the charges? Yes, exactly. So zinc, remember, what is so special about zinc? It is what kind of metal? What kind of transition metal? Fixed charge. And what charge does zinc like to adopt? 2 plus. Okay, I'll show longhand how this works, don't worry. And then nitrate, NO3. Looking at your periodic table, we actually discussed this as a textbook polyatomic ion at the start of this lecture. What is it? What's the charge? Minus. So this is nitrate. And this is zinc ion. Okay, if you didn't have this proprietary information handy, or if you forgot zinc was a fixed charge transition metal, we can approach this using the longhand method. So we take each of our subscripts, we cross them up into our charges, and that in turn, whoops, one moment, gives us zinc 2 plus and NO3 minus. And again, we do a check. Does this match our prediction? Does this match the correct charge of nitrate? Yes, it does, so we're okay. Okay, let's keep going. This one we'll do together. Let's predict the charge of each ion in, and again, I'm not going to say the formal name. This is iron acetate, and I'll tell you the correct name at the end of this. So iron, we have iron, and then we have CH3CO2. What do we call this CH3CO2? What is that? Acetate. And what is the charge of acetate? Yes, -1. So we call this acetate. I don't know why, but the book really loves to write this as C2H3O2-, and that just makes no sense to me from like a structural perspective. Both formulas match that of acetate. I substantially prefer this first formula because it's how you'll see it in organic classes. Okay, so we know the charge, perfect. So we can just use our reverse cross method now. So we have iron. We have one iron, and we have acetate. And we have two acetates. We're going to cross our charges. We're going to reverse cross our subscript up to our charges, just to be 100% clear. And now we end up with iron 2+ and CH3CO2- is all right with the world. Do our charges match the predicted charge for acetate? Yes. You're always checking using your anion because anions are almost always fixed charge. Everyone good so far? Okay. Sorry. Oh, okay. Yes. Please go ahead. We'll just be lecturing. She's not in today.
Do you think we should drop off some flags for her? Because I'm not sure where we're allowed to post it.
Sure. Or if you can also come back Monday if that would also work. Or I can leave them for her. That's fine.
Yeah.
Okay. Perfect.
Just,
Sorry for the interruption. Oh, no problem. Yep.
have a nice day.
Yes, enjoy your day as well. Sorry about that. So, back on track now. We're now looking at a charged ionic complex. So let's look at FeOH4-. So this time, you're going to have to use the original ion charge formula because our total charge is at 0 in this case. What's our total charge? -1. Yep. So take a moment, work on that one. I'll walk around and check to see how you're doing, and then we'll come together to discuss. Any questions? Okay. Yep, that's good. Oh, since this FeOH has a -1 charge, yeah, the charge of iron is going to be a little bit different. But trying to think what charge of iron do you need to have with a total charge to be -1? Yes. Yep, looks good. Okay, I saw a lot of reasonable answers. Let's first talk a little bit about this. So if you're using the formulaic method, your total charge, let me write this over here. Our total charge is what in this system? What's our total charge? -1. So -1 is our total charge. And now we're going to take the number of cation. So what is our cation? What's our positively charged species? Iron. So iron is our cation. So we have 1 iron atom times the charge of iron, the charge of our cation, plus the number of anion. What is our anion? Hydroxide. Okay, and how many hydroxides do we have? 4. Okay, and the charge of hydroxide is -1, right? So rearranging this equation, is it okay if I erase to rewrite it? Okay, I'll rewrite it in the more useful form. The charge of iron is equal to our total charge of -1 minus the charge of our anion, which is -1, times the number of anion, which is 4, divided by our number of cation, which is 1. This is using the original total charge equation. Does everyone make sense on what number is represented in this equation? Any questions on how I got these numbers? Okay, so plugging this into our calculator, this is -1 plus 4, which gives us a charge of +3. So this is Fe3+. Does that make sense to everyone on how to handle charged complexes? Okay. For the last exercise in predicting formulas, not in this lecture session, we're going to fill in the blanks with at least 3 reasonable atomic ions and 1 polyatomic ion. So if we have blank 2 CrO4, I'd like you to provide me a reasonable set of 4 formulas containing 3 different polyatomic ions. Oh, sorry, 3 different atomic and 1 polyatomic. Any questions? Okay. Any questions? Everything going okay? Yes, LGD. Is that calcium? So we'll try to think about the charge of chlorine is 2 ions. Try to think of what Any questions? I think that's perfectly interesting. Any questions? Yep. So you're correct in the charge assignment. Yeah, sure.
Yeah.
How about some main group metals? Transition metals are sort of cheating on that question. They're reasonable, but so what main group 1 would that be? Yep. Okay. Perfect.
That was right.
Mm-hmm. Okay, let's take a look at this question. So first and foremost, the first thing we need to do is establish our charges. So we're going to cross our subscripts up to get a sense of our ion charge. So blank is an ion with a +1 charge. Just to make sure we aren't going too crazy here, chromate is CrO4 2-. If you look up chromate in your polyatomic ion table, what's the charge? 2-. You always have to do this check for your ion charge with the table that you will have memorized by the exam. Okay, so now that we're looking for things with a +1 charge, that makes things a lot easier. So what elements typically adopt a +1 charge? So what cations typically adopt a +1 charge? What group number? 1A. So we're looking for 1A metal ions. So then, what metal ions should we pick? What's an example of a 1A metal? What was it? That's a transition, but we'll put that on the side, yeah. Fe plus is valid. Lithium, yep. What else? Sodium and potassium. I just realized a major design flaw in this question is that since transition metals adopt a variable charge, you can inevitably just write a transition metal and attempt to reach a plausible answer. Although transition metals are technically correct, there are sub-rules in terms of preferred ions for transition metals. So iron plus would be okay, but it's extremely rare to see. What about a polyatomic ion? Ammonium, yep. For polyatomic, we only really have one polyatomic cation that we deal with, and it's the ammonium, derived from the name ammonia. So this is ammonium cation. Perfect. So we can fill in the blanks and generate at least 10 plus unique formulas. Does that make sense to everyone? Okay. Let's keep going now. We're now going to talk about nomenclature, which is the act of naming compounds. How do we go about naming compounds? Because we communicate using words. We don't communicate using chemical formulas. It's very awkward to talk in terms of chemical formulas. So what we do is to convey compound formulas, we have a series of naming rules. So for binary compounds, they have exactly 2 different elements. So binary, exactly 2. No more, no less. They can have any number of atoms, but we just need 2 different elements, okay? Binary ionic compounds are composed of exactly 2 different elements involving a metal cation and a non-metal anion. Okay, so let's look at an example of a few of these compounds. We're going to make some new ones because the ones I gave in the notes are good, but we want more. So an example of a binary ionic compound would be calcium chloride, CaCl2. We have a metal cation, non-metal anion, and we have exactly 2 different elements. Do we have exactly 2 atoms? How many atoms do we have? 3. So binary compounds can have more than just 2 atoms. They can have many atoms, but we only have 2 different elements. Let's show another example. Let's look at another example. So another example would be aluminum chloride, AlCl3. Again, do we have exactly 2 different elements? Yep, but we can have more than 2 atoms. Let's replace chloride with bromide, just so that we have some variety here. Okay. Now, as ionic compounds are composed of a metal and a nonmetal, a metal cation and a nonmetal anion, binary covalent compounds. So covalent compounds are typically composed of what types of elements? Nonmetals, exactly two. So for binary covalent compounds, exactly two different elements covalently bonded. So we have two different non-metal elements. So for example, we have a few here. Other examples of binary covalent compounds would be SO3, sulfur trioxide, other examples would be P2O5, which is diphosphorus. I always forget the H. Diphosphorus pentoxide. And as you notice, the way that I'm naming these compounds is different depending on whether they're ionic or covalent. Do you notice the subtle differences in how I name them? So first we have calcium chloride. Whoops. Just one moment. So we have calcium chloride and aluminum bromide. If we compare our ionic and our covalent names, do you notice how they're different? The naming conventions are different for different classes of compounds. So in order to name something, you must first identify it. Does that make sense? Okay. So, binary ionic compounds, otherwise known as Class A compounds, they're composed of, and let me switch colors for this, a main group metal and a non-metal. So A group elements. So the way that you handle naming these ionic compounds, if they're binary ionic, Class A, you write the name of the metal cation. You're literally just reading it off from the periodic table. You're going to have to know the names of all the metals up to at least the 36th element in the periodic table, if not more. And the next thing that we do is we find and we write the name of our non-metal anion, except we replace the ending after the stem with IDE. Now you may be wondering, what exactly do I mean by stem? Well, each element name, for the purposes of nomenclature, has what's known as a stem, a set of letters that we modify with prefixes and suffixes. So these are all the common element stems that you're going to have to memorize and be familiar with. Now, there are a few unique stems that I want to highlight, as it's often a little bit unintuitive. So for example, oxygen. So oxygen refers to O2. If we wanted to refer to O2 minus, what is the stem for oxygen? Just the stem, ox. So we write OX, and then we add the ending IDE. So this turns into oxide. Let me just zoom in. There we go. Other interesting stems to pay attention to include that of nitrogen. So nitrogen refers to N2. When we're talking about the nitrogen ion, N3 minus, what is the stem for nitrogen? Yep, NITR. And then we replace the stem ending with IDE. Does that make sense? This is how you name atomic anions. So to put this all together, if we wanted to name NaCl, first things first, we write the name of our cation. What do we call Na? Sodium. So Na plus is just sodium. Next, we write the name of our non-metal anion. So what do we call, what is chlorine's stem? Chlor, yep. So we write chlor, and then we replace the ending with IDE. So we have chloride. Does that make sense? Okay. So this full name for NaCl, or table salt, would be sodium chloride. Okay, let's keep going with more practice. Now, suppose you wanted to write the formula of a binary ionic compound from the name. Well, the first thing that we're going to do is we're going to take a look at the formula and we're going to identify the metal cation. Okay, and you can do that just reading off the name and correlating it to the periodic table or the element symbol that you've memorized. Okay, so we're going from name to symbol. Next, you're going to identify the non-metal anion. Perfect. Now, unfortunately, when you're writing the structure from the name, you have to do an additional step. You're going to determine the charge of each component ion. Do we know how to do that from the periodic table and other trends? Yep, so we know how to do that. That's not too bad. And then what we're going to do is we're going to cross our charges. We're going to place the charge of each ion in the subscript for the opposite ion, just like how we generated the formulas of our ionic compounds. As a last step, you want to verify that the total charge of the ions matches the charges of your ionic compound in question. So let's show an example. Potassium selenide. I'll do the first one, you'll handle the second one. So potassium, if we look in the periodic table, I go to the periodic table and I try to find potassium. What element symbol corresponds to potassium if you're looking at your own periodic table as well? K, yep. So potassium is K. Okay, and I'm also going to note the fact it's a 1A element while I'm there, just to be efficient. Selenide, selenide. What element is that representing? Where do you see that prefix? Where do you see that stem? Let's look in the periodic table. Okay, let's go over and we see what element has that stem. Selenium, exactly, right here. And while we're here, just to be efficient, what group number is it? 6A, yep. It is a relative of oxygen and sulfur. Whoops, one moment. There we go. Okay, so we have selenium, and it's a 6A. Now, all we have to do is write our charges. Write our charges. So potassium, as it's a 1A. Oops, let me make that a little more clean. As it's a 1A, what charge does it adopt? +1. Selenium, as it's a 6A, what charge does selenium adopt? Yep, 6 minus 8 gives us -2, so we have -2. We then cross our charges into the subscripts, and that gives us, as a final formula, K2SE. Does that make sense, Daryl? Okay, let's now try one more. I would like you now to attempt this example on your own, and then we'll come together to discuss. Yes. Oh, just right in. Yeah, let's show them that. Any questions? Any questions? Oh, that's it. Any questions? Okay. So, would someone like to volunteer a formula for barium phosphide? Would someone like to volunteer a formula for barium phosphide? Yep. So let's talk about the logic behind this. So barium is a 2A element. Phosphide is referring to phosphorus, which is a 5A element. Writing out the charges, barium adopts a +2 charge. Phosphorus, 5 minus 8 gives us -3. Phosphorus adopts a -3 charge. We cross our charges into our subscripts, and that gives us Ba3P2. That's the formula for barium phosphide. Any questions on that? Okay, we're now going to do a lot of exercises. So the first thing that we're going to do is we're going to do some naming exercises. So for these first 3, I want you to name the following ionic compounds, and as a bonus, I want you to tell me the charge of each ion while you're here. So let's talk about these. Would someone like to volunteer a name for this first species? Calcium iodide, yep. So first things first, we name our cation. So Ca2+ is calcium. Next, we name our anion. Whoops. So if we have I-, so instead of iodine, the ending gets modified to iodide. This is calcium iodide. Does that make sense? Would someone like to volunteer a name for the next compound? Barium sulfide, yep. Where the sulfide is derived from sulfur. In case you were curious about the charges, barium is a 2A element and sulfur is a 6A element. So what charges do we have? What's the charge of barium? 2 plus. And what's the charge of sulfur? Yep, 2 minus. Perfect, perfect. Let's look at one more. ALN, what is that? Aluminum nitride, perfect. And what is the charge of aluminum, given it's a 3A element? Yep, 3 plus. And what is the charge of nitrogen, given it's a 5A element? Yep, 5 minus 8 gives us -3. So we have a 3 minus charge. Always want you to be cognizant of the charges of your ions. Okay, let's now continue on and let's write the formula for the following names. So write the formula given the names. So take a moment to do that and then we'll come together as a group to discuss. Any questions? Okay. Any questions? Okay. Any questions? Okay. Okay, let's continue moving through this. Would someone like to volunteer a formula for lithium sulfide? Yep, Li2S. So just to summarize, lithium, we consider it's Li. It's a 1A element, so it forms a positive charge. Sulfur, as a 6A element, adopts a 2 minus charge. We cross our charges, that gives us Li2S. Does that make sense? Okay, cesium oxide. So would someone like to volunteer a formula for cesium oxide? Yep. CS2O, exactly right. Cesium is also a 1A element that adopts a +1 charge. Oxygen's a 6A element that of course adopts a 2 minus charge. We cross our charges into our subscripts and that gives us our formula for cesium oxide. Does that make sense? Make sure you're writing down your charges and you're using your periodic table. Does anyone have any questions on where I got these charges from? Really don't be shy. Okay, if there are no other questions, we're going to continue on then. So there are some additional practice. As I've seen people were doing quite well, we're going to skip page 29. If you want to practice more on that, page 29 is a good place to look. But we're going to move on to the more interesting ionic compounds, in my opinion, the polyatomic ion containing ionic compounds. And really with nomenclature, you want to make sure your rules are solid for each different type of compound. Because the more ways of naming I teach you, the more what's going to happen is the wires are going to start to get a little bit crossed and people are going to use the wrong naming convention for the wrong type of compound. So just make sure you're focusing on what types of compounds we're naming. We're looking at polyatomic ions. These are ions containing multiple atoms with a net molecular charge. These are our polyatomic ions. You're going to have to memorize them. I talked about rules for naming and memorizing these polyatomic ions, which polyatomic ions should you focus on? What ending suffix should you memorize? 8. Yep. So I'm going to circle. So you really want to be memorizing all of the polyatomic ions with the 8 suffix, and then using the rules that I showed you in order to reduce the formula into other derivatives. So what do I mean by that? The 8, ite, hypoite, and per 8 prefixes are all derivatives of the 8 polyatomic ion. They either have more oxygen atoms or less oxygen atoms. So if you memorize the 8 and you understand what each of these suffixes mean, you'll be able to quickly write the formulas of all the polyatomic ions. So it's a method of saving mental headspace. But it will just come down to memorization. But in addition to the formula, don't forget the charge. A lot of these problems, we need to know the charge of our ions. And if you forget the charge, then you'll just be sitting there trying to write a formula and nothing will happen. So make sure you're memorizing the charges as well. Okay, let's now talk a little bit about how to name polyatomic ion containing compounds. And the rules are quite straightforward. Step 1, you write, oh, this pen's not very good, let's switch. So you write the name of the cation. It can be a metal or it can be a polyatomic ion. Both are fine. Okay, the next step, you're going to write the name of the non-metal anion, retaining the stem, and you replace the ending with IDE only if it's a main group non-metal. Does that make sense? As a side note, if your non-metal anion or cation is a polyatomic ion, you write the name with no changes. Okay? So, let's talk about how we name a few of these compounds. So, CaCN2. So our first step is to write the name of our cation. What's our cation? Calcium. So Ca2+, we'd call this calcium. Okay, now our next step is to identify, do we have an atomic anion or polyatomic? Cn, is that a polyatomic ion? Yes. Okay, so Cn, since it's a polyatomic ion, we're instructed to write the name with no changes. So this would be calcium, and what do we call Cn? Cyanide. Okay, does that make sense? Let's do another example. Actually, let's do another 2, just for practice, as this is often the place where students make very odd errors. So KNO3, what's our cation? Yep, potassium plus. So this is potassium. And is our anion atomic or polyatomic? Polyatomic. What do we call NO3 minus? Nitrate. Okay. Let's now continue on. This case, NH4 to SO4. What is NH4? Is that something? Ammonium. Yep, it's a polyatomic cation, NH4+. So we just write the name. Notice when I say we just write the name, what do you have to know in order to complete this naming process? We have to know the name of all of the polyatomic ions. So that's why I'm really pushing you to memorize and use them in your practice. So SO4 2-. What do we call SO4 2-? Sulfate. ATE. Notice it's 8. It's one of the more common polyatomic ions. Not like in terms of abundance, but in terms of the naming conventions, the 8 is like your starting point. Okay, let's now talk a little bit about hydrogen-containing polyatomic ionic compounds. So in this case, you have hydrogen atoms bonded to, and this is a bit of a dual meaning sentence, they're bonded to a base polyatomic ion. The reason why this is interesting is many of the polyatomic ions you see are Lewis bases, like they function as bases in acid-base chemistry. So I thought that terminology was interesting. So for example, carbonate, if we stick a hydrogen on it, it's named as hydrogen carbonate. Why? Because it has a hydrogen attached, right? Now, a few rules here. Adding a hydrogen atom reduces the charge of the polyatomic ion by 1 per hydrogen atom. A hydrogen atom, you can think of it like H+, okay? So each time you add it to your formula, your charge will go down by 1. So, for example, let's look at a base polyatomic ion. So SO4 2- is sulfate. Let's change things up. What would we call SO3 2-? One less oxygen? Sulfite, exactly. Okay, so that's sulfite. When we're dealing with HSO3, my question to all of you is, what is the charge of HSO3? So each time you add a hydrogen, your charge magnitude decreases. So it's going to be HSO3 minus 1. Because what's -2 plus 1? -1, exactly. We're just adding the charges of both of these ions together. And we would call this, so we take our sulfite name and we would add the prefix hydrogen. Let me make some space for this. So this would be hydrogen sulfide. Okay, let's now do one more example. Let's look at instead of phosphate, let's look at H2PO3. So, what is the charge of PO3? 3-. This is known as phosphite. Notice how we have 8 and ite related by the number of oxygen atoms. Now, if we look at H2PO3, what would we expect the charge to be of this phosphite derivative? Just remember, we start with the 3- charge. We've added 2 hydrogens. So our charge will get smaller in magnitude by how much? 2. So then what's the charge of H2PO3? Just -1. Does that make sense to everyone? Because if you're not able to calculate the charges of these hydrogen-containing polyatomic ions, all the formulas that you generate will be completely off. For your reference, this is called dihydrogen. Let me make some space. This would call dihydrogen phosphite. Di for 2 hydrogens. So, how do we name hydrogen-containing polyatomic ions? What's the process? First and foremost, we are always considering your polyatomic ion base. So in this case, we look for our polyatomic ion. In this case, we have PO3, 3 minus. And what do we call that? What do we call it? Phosphite, exactly. One less oxygen than phosphate. Okay, we've completed that step with flying colors. Wonderful. So we have PO3, 3 minus, so this is phosphite. Okay, let's see what we have to do next. In the name, you're literally going to write the word hydrogen in front of the name of the polyatomic ion. So I'm going to do just that. So hydrogen and then phosphite. Okay, so what we have now, PO3, 3 minus, and our name is telling us we have a hydrogen, so our charge changes. Now, if there are 2 or more hydrogen atoms, we need to use a prefix. And these prefixes are derived from Greek and Latin to specify the number of hydrogens. So we write a prefix that tells us the number of hydrogens in front of the word hydrogen. So the one for hydrogen containing polyatomic ions, the only major prefix that comes up is di, which signifies 2. So if we look at our original formula, how many hydrogens do we have in this formula? 2. So what prefix do we use? Di. So this would be di hydrogen phosphite. So this is the whole name for a single hydrogen containing polyatomic ion. And let me label how each part of the name tells us how to construct the formula. So H, hydrogen, 2 for di, phosphite for the PO3. The charge you have to adjust manually. That's just something you have to do. Does that make sense? Now, this whole thing is a polyatomic ion. So to complete our name, if we're looking and we have NaH2PO3, so we have this sodium cation in front. Just like our rules for naming polyatomic ion containing ionic compounds, what's the first thing that we write in the name? What's the first thing that we name? The metal or the cation or the anion? Cation. So this would, so NaH2PO3 would be sodium. Yes, dihydrogen phosphite, exactly. There we go. Does that make sense? Each of the pieces we've learned before, we're just applying them in different ways. Now, I do have to give you a warning on this because sometimes people get a little overzealous with these rules and start to apply them to molecules that are not polyatomic ions. So by definition, polyatomic ions, do they have a charge? Yes. So then, if a polyatomic ion contains hydrogen and is neutral, it is not a polyatomic ion anymore. It's an acid. So looking at H2SO4, this is known as sulfuric acid. I would like you to take a look, and I'm going to show you for comparison HSO4 minus, which is named as hydrogen sulfate. Does everyone notice the dramatic shift in how these two species are named? Because what has changed? The polyatomic ion has what? A charge. It's just a charge in general. While the acid, does it have a charge? No. Acids are neutral. Just really be careful about that. Why? As you've seen, are acids named differently? Yes, they are. Okay, let's continue on now. We're next going to talk a little bit on how to name ionic compounds that contain a variable charge transition metal. So transition metals can adopt a range of positive charges, right? So if we're looking at iron, we can have anywhere from iron plus to iron 2 plus to iron 3 plus. Now, because these transition metals can adopt a variable charge, the charge of the transition metal ion must be explicitly noted to avoid ambiguity. So what do I mean by that? How can this cause problems? If you said, for example, iron chloride, do we know the charge of iron immediately from the name? No. So then we can come up with at least 3 different formulas for each of the different charges. So this could mean FeCl, FeCl2, FeCl3. Well, that's not very useful. A name should refer to one thing and one thing only, especially with regards to chemistry. So in order to relieve this ambiguity, the charge of the transition metal ion will be explicitly noted. So for example, let me switch pen colors here. So for example, we go iron, then in parentheses, using a Roman numeral, we'd specify our charge. So for example, iron 3 chloride would correspond to FeCl3. Now, before you look at this a little bit too much, this 3 and this 3 are not the same, okay? The 3 is not telling you the number of chlorines. The 3 is telling us the iron charge. So we have Fe3 plus, Cl minus, we cross our charges, and that's where we get FeCl3. Does that make sense? I just really don't want people to get confused and think this means the number of anion. It's not. It's the charge of your metal. As you see, including these Roman numerals makes it explicit what compound we're referring to. Okay, let's keep going now. So here are the rules for naming ionic compounds containing variable charge transition metals. So first thing that we're going to do is we're going to write the name of your transition metal cation. So for example, Fe, you'd call this iron. Now, to delineate the charge and specify the charge, what we're going to do is we're going to write a Roman numeral after the name of the transition metal cation, indicating the charge of the metal cation. Here are each of the Roman numerals up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Have we seen Roman numerals before this class? If not, I would focus on practicing with them and just making sure you're comfortable using them, because Roman numerals are used to specify the charge of your transition metal cation. You can't just put a number 2, as that has an entirely different meaning. Okay, now If your anion just so happens to be an atomic ion, for atomic ions, atomic anions, what do we change the ending to? IDE, yep. So like Cl minus is chloride. Yeah. If you happen to be dealing with a polyatomic ion, you just write the name with no changes. So polyatomic ions are easier operationally, but they have a bit of a memory burden. Okay, let's take a look at this example. And I chose this specific example because it really highlights you still need to be careful that you're following charge rules. So FeSO4. Before I even start to try to name this, the first thing I'm going to do is figure out my charges. So it's Fe1SO41. I reverse cross my charges. And what is our charge of iron just at the onset? Yep, the charge of iron, if we cross the subscript up into the charge, is Fe plus. Now, things all seem fine and well until you take a look at sulfate, SO4 minus. Now, I've seen as a common mistake on the exams, students just go, looks fine to me. Is this correct? No. What is the actual charge of sulfate? 2 minus. So then, as per our charge adjustment rules, what do I have to do to each of these charges? Multiply by 2, because 1 times 2 gets me 2. So then, at the end of the day, we end up with a charge of iron of Fe2+. Perfect. Does everyone understand the work involved to get the charge of iron? You're going to have to do that for every single one of these problems. So now we're ready to name this. Okay, so I'm going to write the name of my cation, which is iron. And now this is where all this work has led up to. What's the charge? 2. So we put a Roman numeral 2. And then finally, we name this SO4. What do we call SO4 2 minus? Sulfate. There we go. Does that make sense? Perfect. Don't forget the Roman numeral or you'll get 0 points in naming for these types of questions. Okay. Now, this is an important point. Remember how I talked a lot about fixed charge transition metals, how I mentioned there were a few transition metals that adopt only a single preferred ion charge? Well, silver, cadmium, and zinc, you do not have to specify the charge of the transition metal for a fixed charge transition metal because it's fixed. There's no ambiguity, right? If it only makes one ion, you don't need to specify what ions generate. So then, as a result, let's take a look at the following compound. So if we're naming this, we name it exactly like your bread and butter binary ionic compound. So what's the name of our cation let me write it out. I heard the correct name, but let's talk about the 2 pieces involved. So we have our cation, which is zinc 2+, which we name as zinc. And then our anion is I-, and what do we call I-? Instead of iodine, it would be iodide. This would be zinc iodide. And again, we don't have to put the Roman numeral specifying the charge because it's a fixed charge transition metal. Does that make sense to everyone? Okay, let's do some practice. So what I'd like you to start off on is naming these first 3 compounds. And then let me switch. There we go. Perfect. And I'll be walking around and checking to see how everyone's doing. Any questions? Any questions? question. Okay. Since copper is a transition metal, I should have specified the charge. Yeah. How is the sulfur equivalent -2 or -1? Everything going okay? Just make sure you're checking. So the sulfur to be about -1 or -2. So then you have to adjust both of the charges. Okay, let's take a look at a few of these, and I've hidden a few trick questions in here. The first one is, it looks easy, but it's more tricky than it appears. So before I even do anything involving naming, I figure out my charges. So Cu1S1, I cross my charges, and that gives me copper plus and S minus. Does that look okay to everyone? No. No, we're going to need to adjust the charges of both our cation and anion because the true charge of sulfur is 2 minus. So let's multiply both of our charges, keyword both of our charges, by 2. And that in turn gives us copper 2 plus. Okay, so how do we name this? What's the name of our metal? Copper. Yep, and then you place the charge in parentheses in Roman numeral. So Roman numeral 2. And then we write the name of our anion, in which case it's S2 minus. What do we call that? Sulfide, exactly. Okay. I can see people are getting a little bit fatigued. So what we're going to do is we're going to pick this up next class session. We'll finish chapter 3 next session, as everything towards up to the end of chapter 3, you're responsible for on your exam.